Hi everyone, this is Ipsitha from Assistant Professor from Civil Engineering Department of St. Peter's Engineering College. Today we will discuss about the structural element beam. As we all know that in a construction, the horizontal members constructed in a space or in between two columns is known as beams, and the vertical members are known as columns. Now, if we consider a room where at the all the four corners, there are columns, then the horizontal member at the roof level is known as your beam. This is beam, and these are columns. A beam is constructed to carry all the load at the load falling on it and transfer it to the column, which in turn transfer it to the soil. There are different types of load acting on a beam. Now, beam have its own self weight, which is known as dead load. After that, we have live load, we have wind load, earthquake load. Different types of load acts on a beam, which in turn transfer it to the column. The column transfer the beam to the soil. Now, there are different types of load. As per that, the first type of load which acts on a beam is your dead load. Dead load is nothing but the self weight of the beam, or whatever constructed load or wall load, slab load which is coming to the beam is known as your dead load. Now, if this is a section, the load if we construct any wall above the slab, then that load comes on the beam. Then the load of the slab, the own structural load of the beam, all comes on this structure. That is known as your dead load. After dead load comes your live load. The load of the temporary structures or temporary materials are known as your live load. It can be we can be all the humans, students, anyone, or the furniture, extra materials, whichever are put on the slab or on the roof is considered as live load. After our live load, then comes your wind load. Wind pressure, or the force applied by wind on the building or any other structure, is known as your wind load. Actually, wind load acts laterally. If we take a section, the load acting horizontally is known as your wind load. In live load and dead load, the load acts vertically downward. It acts vertically downward. Or it acts on gravity. But wind load acts horizontally or laterally. Another big load which has been considered as per zone or location of a structure is known as earthquake load. So earthquake load actually works, it's applied on the below the bottom when the earth vibrates due to seismic vibration, due to when the plates of the earth move, there is seismic waves, vibration on the earth surface. This vibration shakes the bottom of the earth, then the total structure vibrates. This is known as earthquake load, which also acts laterally or horizontally on the bottom of the structure. So wind load and earthquake load mostly makes the building shake, or it bends the column or the structure, or it also leads to collapse of the building. As per specific location, as per specific area, we have snow load also. Snow load is the load of snow on the roof of a building. And we also have water pressure, which acts on dams, water tanks. This also acts horizontally like this. Snow loads acts vertically on the surface. So these are different types of load. Mostly when we are designing or analyzing, we will take all the loads up to earthquake. We will take up to here and take the specific dimension, take the specific areas, then as per code how much live load will be applied to residential building, or how much earthquake load, wind load will be applied as per the zone or area we are staying. As per that we will do the analysis. After analysis we will do the design. Now what is analysis? Analysis is we have to find out what are the load acting on a structure, what are the forces acting on a structure, what is the moment, what is the bending, how much it may deform if those loads are applied. That is known as analysis. Next part is design. Design is to find out the dimension of the structure, to find out how much length, how much width, how much depth should be provided on a structure to take the external forces, so that the building doesn't break or collapse, or it can be durable, sustainable for a long time. Now let's go to the let's go to beams. So there are different types of beams structurally. Structurally, there are different types of beam. In this first is singly reinforced beam, then doubly reinforced beam, cantilever beam, T-beams, flange beams. So today we will first discuss about singly reinforced beam. Singly reinforced beams. We know that in RCC or in reinforced cement concrete, concrete is the main part. But concrete is very strong in compression force, but it is weak in tension. What is compression? Compression is the force which we apply to reduce, like this. When we are applying on a structure or any body, when we are applying or pushing it inside, is known as compression. When we are pulling a force together like this, it is known as tensile or tension. So concrete is very much strong in compression, but it is weak in tension. That's why we are using reinforcement, or we are using steel. So in a single reinforced beam, the reinforcement is, or the main steel is provided at the bottom. Only one reinforcement is provided at the tension zone or tensile zone. In a beam cross section, if we consider a beam cross section, the neutral axis is at the center, where the neutral axis is at the center where the tension is equal to compression. So, if we consider this neutral axis, the tension force is acted by the reinforcement, which is denoted by T, and the compressive force is acted or taken by concrete, which is denoted by C. So, in the neutral axis, C is equal to T. So, in a single reinforcement beam, we have only reinforcement provided at the bottom or at the tension side, tension zone. Next, if this is the total surface is taken, total depth of the beam or section is taken as D, the width is taken as B. And we can, this is cross section, we can also draw a longitudinal section for better understanding. If we draw a longitudinal section, the corners are the support. This, the beam supplied at the end, is known as your this is the main reinforcement. So, this is main reinforcement. Okay, and this is the cross section. This form the support. Clear distance between the two support is known as clear span. The clear distance between the two support is known as clear span, and the center of the support to the next center of the support is known as your center to center distance of the beam. So, while designing or analyzing, we require this measurement, center to center of the distance between the two beams, the clear span, depth of the beam, and the width of the beam. Another thing we should know is cover. There is, when we are placing the reinforcement, between the reinforcement and the bottom of the beam, there is some clear space, which is provided for the reinforcement to, is provided so that there is no extra or your what you say temperature or your climatic, needs no problem from the climatic exposure. There is mild or moderate exposure. So, we provide clear some clear cover to the beam. The distance between the clear cover and the center of the beam is known as your effective cover, and from the center of the beam to the topmost fiber of the beam is known as your effective depth. So, these are the parameters we require for planning or designing a singly reinforced beam. So, first part, another part in a singly reinforcement beam, or while designing or analyzing a singly reinforced beam, we will consider is the materials. First is the materials what we are taking. As it is a reinforced cement concrete or reinforced concrete structure, so concrete is the main part, then is the steel. Concrete we will be using is cement concrete of nominal mix or nominal proportion of M20 or M25 or M30. We can go to higher grades as per the requirement of the structure. M20 is mostly 1:1.5:3. M25 is 1 is to 1 is to 2. From M20 we have to do the mix design, which comes again in concrete technology. So what is 1 is to 1.5 is to 3? 1 part of cement is mixed with 1.5 part of sand or fine aggregates, and then mixed with 3 parts of stone chips or coarse aggregate. Same thing for M25. It is 1 part cement, 1 part sand and 2 parts of coarse aggregates. From M20 mix design, above M25, we have to again recalculate the proportion. These are the proportions. These are mix. Next material used is steel. In steel also we have mild steel. Mild steel, the yield strength, Y-I-E-L, yield strength is Fy 250 Newton per mm square. Then we have mild steel, this is Fe 250. Then we have Fe 415, where the yield strength is 415 Newton, 415 Newton per mm square. And Fe 500, where Fy is equal to 500 Newton per mm. In this concrete mix proportion, the strength is denoted by FCK. So FCK of M20 concrete is 20 Newton per mm square. And for M25, it is 25 Newton per mm square, and 30 it is M30, it is 30 Newton per mm square. Actually M20, M25, M30, M means the mix proportion, 20 is the strength of the concrete. If we go for lesser values, it can be M15, where M is the mix and 15 is the strength of the concrete. So this is first step is materials. After materials, we will go to neutral axis or finding the depth of neutral axis. Depth of neutral axis, XU. If I draw the beam again, so the center point is known as XU. The beams are placed here. The depth of the beam is, effective depth is small u. This is small b. So XU value have to be calculated. There is a formula in XU. XU is equal to 0.87 Fy AST by 0.36 FCKB. So here 0.87 FCK Fy 0.87 Fy. Fy is the yield strength of the steel used. If we use FEF 250, it will be 250 Newton per mm square. If we use 500, it will be 500 Newton per mm square. AST is the area of the steel, whatever steel area we are using, and 0.36 FCK BD. FCK is the strength of the concrete use, B is the width of the beam, D is the depth of the beam. After finding out the XU value, we have to find out if it is a balanced section or an over reinforced section or an under reinforced section. In balanced section, the compressive strength, whatever is coming, the compressive strength the compressive strength T should be equal to the compressive strength C should be equal to T in a balanced section. So we should always prefer balanced section where the compression strength is equal to the tensile strength. Under reinforced section, the compressive strength is less than the tensile section. But this structure is okay because tension is more, the tensile strength in the structure is more, so it can take extra load also. But when we go to over reinforced section, there the compression strength C is more than T. Compression strength is more than the tensile strength, and it leads to the failure of a structure. The compression falls. Now let us do a small problem. The problem is, let us consider a rectangular beam of 400 mm to 800 mm provided with 4 numbers of 20 mm dia bar. The grade of concrete is already given, M20, grade of steel is given as 500. Now determine the moment of resistance. For moment of resistance, we have a formula mu is equal to 0.36 XU into D minus 0.42 XU into FCK into B, where we know XU is depth of the neutral axis, then D is the depth of the beam or effective depth of the beam. Effective depth of beam, FCK is the compressive strength of concrete. B is the width of the beam. So if we write given is, already it is given is B is 400 mm, D is capital D or overall depth of the beam is given as 800 mm. Let us consider clear cover. Mostly for beams we use clear cover as 20 mm. So if we consider clear cover as 20 mm, effective depth or small d, effective depth D is equal to capital D minus effective depth D minus dia of the steel by 2. So let us once again draw the beam, where if we draw the reinforcement, there are 4 numbers. So let us draw 4 numbers of 20 mm dia. So half of the dia is 10. Small d is from the center of the diameter of the steel to the topmost section. And this is B. B is already. So effective depth is capital D is given as 800. Clear cover we have considered as 20, and this is 20 dia by 2 is 10. So it gives us 730 mm. 730 mm is the effective depth. Next we will go to the find out the neutral axis. Neutral axis is XU. XU is equal to 0.387, sorry, 0.87 FYAST by 0.36 FCK into P. So this is the neutral axis. We will find out 0.87 Fy. We know it is given in the question. If we see, if Fy is given is, the steel is Fe 500 and the grade of concrete is M20. So when we go, we have Fy is 500 Newton per mm square. FCK is, as it is M20 grade concrete, so 20 Newton per mm square. P is already given as 400 mm. One more thing we should find is AST. AST is nothing but area of steel. Area of steel. Area of steel is, it's as it is a circular bar, we can take pi by 4. It's a circular bar, so pi by 4 into d square. Dia is 20 square. There is 4 number of bar, so into 4. Okay, so ST is, this is the diameter. This is the diameter. Pi by 4 into pi 20 square is 20 is the diameter, pi by 4 20 square is the area of the circle, into number of bars are 4. This is 4 4, if we cancel it is pi into the 400 square gives 1256 mm square. So this is the area of the steel. Into Fy is 500 to 56 by 0.36 into 20 into 400. So we will find out the XU. After finding the value of XU, we can find out the moment of resistance or MU. Moment of resistance is known as MU. It is the amount of stress or amount of resistance the structure can take. We know the formula. The formula is written. It is 0.36 XU D minus 0.42 XU FCK B. So let us write it. FCK into B into E minus 0.42 XU into D. So 0.36 into 20 into B is 400. D is, this is the effective depth which we have calculated in the earlier portion. D is equal to 730. So 730 minus 0.42, whatever XU value we will get is some 198 mm or 197 into 197 into D is your effective depth of 730. In this process, we will get the value which is Newton mm square. So this is the process in which the problem is solved. I hope you understood how to do the analysis of your singly reinforced beam. After finding the after doing the analysis, the next part is to find the depth and beam, or to check whether they are okay. That is the design part we will discuss in next class. Thank you.